Welcome to the first lecture on the course of about information security. This is an introductory course and lecture within the scope of the lifelong learning courses in the LMPI Erasmus Plus project. My name is Manuel Fernandez Veiga, and I'm an associate professor from the University of Vigo, Spain. This is the outline that we will cover during this lecture. We will define formally what encryption is at the first place. We will explain the concept of perfect security. We will talk about semantic security and the notion of computational ciphers. And finally, we will present a generic model for information theoretic secrecy. This is the set of fundamental concepts for speaking properly and rigorously about encryption and security, and it forms the fundamentals and the basics for understanding in strict terms what security is, how security can be strictly defined, and to reason in formal terms about the security properties of a given system. So let's start with reviewing the basic definition and notions about encryption. Let's try to understand what encryption is, how encryption works, and what type of ciphers and encryption systems exist. Encryption is the word we use for speaking about message secrecy. When we speak of encryption, we intend to transmit a message between two parties, one sender and one receiver, in a way that no third party can understand or discover the meaning of the message transmitted between the sender and the transmitter. So anyone else can access to the contents, to the real meaning of the message transmitted between the two parties. When ensuring encryption for a communication system, we assume that the channel is completely open, so any third person or third party can see the message transmitted through the channel, but can even capture or duplicate the messages. But the condition for encryption to work correctly is that no one can decrypt the message and get the ultimate meaning of this communication between the two entities. In this lecture, we will cover the formal definition of secrecy, distinguishing between perfect and semantic security. We will see some techniques for single message encryption, that is, for encrypting one unique message between one sender and one receiver, and we will define secrecy games or adversarial attacks to specific ciphers. First of all, ciphering is a mathematical operation. For encrypting a message between one transmitter and one receiver, we represent the message as a sequence of symbols from a finite alphabet. The finite alphabet is typically the binary alphabet, composed of a string of zeros and one, and as such, ciphering is a form of coding between two parties, one sender and one receiver. For the encryption system itself, the fundamental notion is that of a Shannon cipher. Let us define next what a Shannon cipher is. For us, for encrypting along a Shannon cipher, we set up a pair of functions, an encryption function E and a decryption function D, with the following requirements. The encryption function takes a key from a given alphabet, K, a plaintext, which is the message to be transmitted, M, from a suitable alphabet M, and outputs a different sequence of symbols, which we call the ciphertext. The symbolic representation of the ciphertext is like the output of the function E parameterized by the key and the plaintext M. Correspondingly, the decryption function takes a key and a ciphertext, sequences of symbols both, and outputs a plaintext. The requirement, of course, is that the decryption function acts like the inverse operation to the encryption procedure, so that if we apply the decryption function to the encrypted message, we recover the original plaintext under the use of the same key. Note that this definition is completely general and specifies two different algorithms for encrypting and for decrypting. In some cases, we will see this in several examples. In a moment, the encryption and decryption function can be the same, but actually it is better for the definition to assume that the encryption and decryption operations can be different. Also, note that in this definition for a Shannon cipher, the key is an element of information shared by both parties, the sender and the transmitter. So they both need to know the key before the communication takes place. It is for this reason that this kind of ciphering procedure is also known as symmetric encryption or symmetric ciphers, because both parties need to agree before the communication starts the value of the secret key, which must not be revealed to any third party. Let me give you some remarks about this definition. As I said before, the key is a secret element or piece of information. Note also that the definition of a Shannon cipher is completely operational. We are not speaking about any specific encryption algorithm or any specific decryption algorithm yet. We will see examples right now. We also assume that the ciphertext, which is to be transmitted between the sending point and the receiving point, is not going to be altered or tampered during transmission. So we give the third party the capability of inspecting or seeing, watching the channel, eavesdropping the messages, so to say, but not modifying the message to be transferred in this process of operation. For understanding what security is in an encrypted system, we need to understand that the third party, since he can watch the messages, is trying to decipher or understanding the meaning contained in that message. And intuitively, saying that a system is secure after encryption means that no third party can take advantage of knowing the true or the real message other than guessing randomly, because the secret key is kept secret all the time. We will specify this in a moment in a more formal definition, but for now it is enough for us to understand that secure communications is about not having a probabilistic advantage different than random true pure guessing in trying to recover the plain text without knowing the key. Before proceeding further, let me put you some examples of real systems which can be used for encryption and are very simple too. My first example is the classical one-time pad. For this example, let us assume that the key space K, the message or plaintext space M, and the ciphertext space C are strings of binary digits with length L. So we are talking about L-bit sequences. The one-time pad is the encryption procedure which takes a key, secret key, which is a string of L-bit sequence of L bits, and performs the bitwise modulo 2 or binary addition between the key and the plaintext. That's the meaning of the plus sign enclosed in a circle. For decryption, we take the same key and perform bitwise addition in binary field with the ciphertext. If you combine the decryption algorithm with the encryption algorithm in this way, since binary addition is a self-complementary operation, you can see easily that the original plaintext can be recovered. Please note that in this example, the one-time pad, the encryption and decryption algorithms are exactly the same. They are the same operation in one case with the plaintext and in other case with the ciphertext. This is not entirely usual, but for this example works perfectly. Note also that for the one-time pad, the length of the key or the size of the key space is exactly the same as the length of the plaintext and the ciphertext. So the key has to be of equal length, L bits, as the plaintext and the ciphertext to be produced. The The one-time path is very simple, and the name one-time path comes out from a specific property that we will cover in this same lecture after a while. My second example about a simple encryption algorithm, which is also a Shannon cipher, is called the variable length one-time path. In this case, our key space is a sequence of L bits, a string of length L. For the message and ciphertext space, we take strings of length at most L bits. So the message can be shorter than the total key space. The difference between the variable length one-time path and the original one-time path is that now we are allowing for different sizes for the key chosen and the plaintext chosen. Which, in other words, we are considering now that the plaintext can be of arbitrary length, bounded, upper bounded by a given parameter L. The operations with the variable length one-time path are very similar to the original classical one-time path. In this case, we pick first a key and we truncate the key to the exact same length of the plaintext. And the encryption operation consists of performing the binary addition bitwise between the shortened or the truncated key and the plaintext. This is symbolized in the equation you can see in this slide for the encryption algorithm. For the decryption operations, we perform exactly the same mathematical combination between the truncated key and the ciphertext. So the operations in the variable length one-time path are exactly the same as in the one-time path, but with the messages properly adapted to match the plaintext length. Again, it's an easy exercise to verify that the encryption and decryption algorithms satisfy the correctness property. I mean that the decryption function is the exact inverse of the encryption function, and that after applying decryption, one can easily recover the original plaintext after knowing the key. My third example is also a classical example in every encryption course. It's the substitution cipher. For this example, let's assume that we work with a finite alphabet A, and now put or choose for the message or plaintext space and the ciphertext space all the sequences taken from symbols in the alphabet A with length exactly L. Also, for the key space, imagine that we take the set of all the possible permutations on the finite alphabet A. So the number of permutations grows very fast, very quickly, with the number of elements in the alphabet A, and this means that the key space quickly becomes very, very large for this example. For a substitution cipher, the operations for encrypting and decrypting are the following ones. The key for encrypting is simply a randomly chosen permutation on the chosen alphabet A. The plaintext is again a sequence of finite length L taken from the alphabet A. The encryption operation consists in applying the permutation to each one of the elements in the plaintext. So we apply the permutation sigma to the first element, m sub 1, next the permutation sigma on the second element in the plaintext, m sub 2, and so on until finishing with the last element in the plaintext. For decryption, you can easily imagine that we can recover the original plaintext from the ciphertext by applying the inverse permutation element-wise to each of the elements in the ciphertext vector. In formal terms, The definition for the decryption function is the one you can see in the slide, just next to the encryption function, and it uses as key the inverse permutation used for encrypting the original plain text. Once again, it is a very easy exercise to verify the correctness property. That is, that the decryption is completely the inverse function of the encrypting operations. So you can recover the original plain text in one single step, and the power of the substitution cipher comes out from the fact that many modern block ciphers, which are used in real applications and in many security settings, for example, the algorithms AES, Advanced Encryption Standard, or DES, are in fact sophisticated forms of substitution ciphers. The power of this particular encryption or Shannon cipher is that the size of the key space grows, as I said before, very fast with the number of elements in the finite alphabet A. Recall that we are taking as key for this particular example the set of possible permutations defined on the set A, and the number of permutations grows exponentially with the number of elements in the finite alphabet A. We can put some numerical examples after a while, after covering the next example. My last example of elementary or simple or introductory Shannon ciphers is called the additive one-time pad, and it is again a variation of the one-time pad idea. In this case, we pick for the key space, the plaintext space, and the ciphertext space, the same set, which is the set of integer numbers less than n. In other words, the numbers 0, 1, 2, etc. until n minus 1. For encrypting, we simply take a key. A key is a random number chosen from this set, and perform modular arithmetic by adding the key, which is an integer number, remember this fact, and the plaintext, which is to be interpreted as an integer number too. We perform this addition modulus n in finite arithmetic. Finite arithmetic preserves most of the mathematical properties of additional arithmetic, of usual arithmetics, and the decryption algorithm works by using the same key and performing modular arithmetic between the key and the ciphertext to recover again the original message. So in this case, like in the one-time pad in example number 1, you can see that the encryption and the decryption algorithm are exactly the same. And of course, the correctness property is satisfied also here for the additive one-time pad. So comparing example 1 and example 2, the different versions of the one-time pad, you can see that in this case, the only change is how to define the operation, the particular operation, the specific operation for encrypting and decrypting. But the general properties are exactly the same. You can also note in this example, this is an important remark, that the additive one-time pad can also be seen or interpreted or understood as a substitution cipher. In fact, the operations for encrypting and for decrypting are, in mathematical terms, bijections. They are one-to-one mappings between the plaintext space and the ciphertext space. This is also a common property to all the previous examples, but in this case, it is of fundamental importance to understand the characteristics, the features of the additive one-time pad. The ciphers used in real applications are, of course, much more sophisticated and complicated than these ones, but almost all of the modern cryptography systems are built upon these basic building blocks. So it is important to understand substitution and one-time path examples before progressing further. Let's move now to define in formal terms what we understand as perfect security. In proper terms, there are many ways to define what security means for a given communication or storage system. Part of the problem is to understand the meaning and the consequences of defining security in one form or in another form. The starting point for us in this lecture will be to explain first the idea or the concept of perfect security, which is the strongest and ideal notion of security in a communications or storage system. As an ideal concept or definition, this is not always realizable or possible to achieve. We will see some positives and some negative results about perfect security. But before coming to that, let me explain briefly what perfect security is with a formal definition. For understanding perfect security, assume that we are working with a Shannon cipher, that is, with a pair of algorithms, an encryption algorithm and a decryption algorithm. We say that this system is perfectly secure if for any two different plaintexts M0 and M1 and a given ciphertext C, we have exactly the same statistical distribution about the probability of seeing the ciphertext for the two plaintexts. In symbolic terms, the probability that the encrypted message using a random key of the plaintext M0 is the ciphertext C is exactly the same as the probability of encrypting with a random key the plaintext M1 and having the same outcome, the ciphertext C. In this formula, the key is randomly and uniformly chosen from the key space K. Since the definition is not at all clear in strict symbolic or formal or mathematical writing, let me give you a different view of what perfect security is. We speak or we say that the system is perfectly secure if a third party, an eavesdropper, cannot distinguish effectively between two different plaintexts, M0 and M1, just by looking at the ciphertext Z. So, imagine that a third party is watching a communication channel and captures a ciphertext C, and he tries to guess whether this ciphertext is the outcome of encrypting one plaintext M0 or a different plaintext M1. If he has no advantage other than randomly guessing equally between the two alternatives, we say that the system is perfectly secure in statistical terms. Please observe that this definition of perfect security is given as a probabilistic definition. We say that no third party has probabilistic advantage in deciding in favor of one of the plaintext or the other plaintext. So from his point of view, the two chances, the two possibilities are exactly the same, which is what will happen if he had no previous information about the symmetric key, of course. And that the requirement in the definition is quite strict. For perfect security, we are enforcing that the probability of the two events is exactly the same between the two plaintexts. Note also that in this definition, the choice of the two plaintexts M0 and M1 is completely arbitrary. We can pick any two possible plaintexts for speaking about perfect security. In other words, the property, the mathematical property included into the definition of perfect security must hold for any pair of possible plaintexts, or in other words, for all the possible plaintexts. There are many examples of real systems for encrypting which are perfectly secure. You can verify the terms of the definition directly or reason in an alternative way why these systems are actually perfectly secure systems. For example, the one-time path is perfectly secure. It is not difficult to verify that the one-time path satisfies the conditions imposed by the definition of perfect security. In a similar way, you can easily prove that the substitution cipher is also perfectly secure. So the second of our four examples also fulfills this requirement. Similarly, the additive one-time path can be proved to be perfectly secure too, exactly using the same reasoning as in the two previous cases. However, We have seen 4 examples before in this lecture, and there's one of those systems which is not perfectly secure. Specifically, the variable length one-time path is not perfectly secure, somewhat contrary to intuition or to common sense. Why is this so? What is the reason because the variable length one-time path is not a perfectly secure system? Well, the explanation lies in the fact that in the variable length one-time path, the third party can learn something about the plain text just by watching the ciphertext. Specifically, the third party, the eavesdropper, can learn the length of the plain text just by counting the number of symbols in the ciphertext. Recall that the ciphertext and the plain text in the variable length one-time path have exactly the same length, and this length is not the same for all the plain text. So we can distinguish very easily between 2 different plain text just by counting or by measuring the length of the ciphertext. Imagine, to continue with a particular example, that we choose in the definition of perfect security 2 plain texts M0 and M1 which have different lengths. Then, by watching at the length of the ciphertext, we can say without doubt which one of the plain text has been encrypted by the sender for transmitting to the receiver. In this respect, the variable length one-time path does not comply with the strict definition of perfect security and cannot be considered a perfectly secure system. Despite its simplicity, this case, the variable length one-time path is not a perfectly secure system. However, the rest of the examples are easily proven to be perfectly secure. And this means, as an immediate consequence, that perfect secrecy is possible and is very easy to achieve. There are very simple procedures for encrypting and decrypting which are perfectly secure. And this seems to solve the fundamental problem of encrypting and providing security to a communication system in these terms. Because if we can apply one of those simple schemes or procedures to manipulate our messages, are hiding the information or the message they contain, then we have solved all our secrecy requirements. But the answer is not so easy as you can imagine when talking about security in communications and storage. Because there's a fundamental consequence of imposing perfect security on our encryption system. The formal result is known as Shannon theorem for secrecy systems and establishes the following fundamental fact. Assume a given Shannon cipher, a pair of encrypting and decrypting algorithms, and suppose that this system is perfectly secure. Then, as a consequence of the fact that the system is perfectly secure, the key space has to be as large as least as the message space. This is the statement of the Shannon theorem, which we will not prove in this lecture. Actually, the proof is not very difficult, and you can find it in any textbook, in any standard textbook on cryptography, but the interpretation of this result is of fundamental importance for us. I repeat again the statement. What Shannon theorem is telling us is that for achieving perfect security, we have to use keys with length as large as the message to be encrypted. And we have to use those keys only once, only one time. Because using the same key 2 or more times for encrypting different messages is not perfectly secure. This seems to be a contradiction because we don't want to go into the complications of choosing a different key for encrypting different messages every time. Just imagine that our goal is to transmit a very long message between the sender and the receiver. Let's say the contents of a book. For encrypting in a perfectly secure manner this message, we need a key as long as the message to be sent. And this key can only be used for that particular message. For a subsequent communication of a different message, we should pick a different key with the proper length again. And remember that we haven't solved yet the problem of agreeing the key between the sender and the receiver, which must be done beforehand the communication takes place. So this Shannon theorem seems to be quite negative for our purposes, because it forbids the possibility of achieving perfect security in practical terms. After all, in a real system, we don't want to go into the complications of choosing one key for every possible messages, and with possibly arbitrarily long number of symbols. Actually, Shannon theorem is more powerful than this statement shows, because it speaks not only of the size of the key space and the message or plaintext space, it speaks about the entropy of the space. Entropy is a notion taken from information theory, but it is not necessary to understand entropy to follow the meaning of perfect security and the Shannon theorem. So far, we have seen that perfect security is the ideal notion of security. It is the strongest one, because it gives no power to eavesdropper or third-party users who might be watching the channel, in that they cannot gain any advantage by trying to decide between two different plaintext, seeing only the ciphertext. But on the negative side, perfect security is hard to achieve in reality, because it imposes a fundamental limitation on the size of the key space, which has to be as large as the plaintext or the ciphertext spaces. So for designing practical encryption and decryption algorithms, we should relax somehow the strict definition of perfect security and content ourselves with a with a weaker definition of security for practical purposes. This modified definition of security is called semantic security, and it involves the idea of a computational cipher. Let's look closer to what semantic security is, and how a computational cipher can be defined in this context. The main consequence of Shannon's theorem is that perfect security is a correct notion of security, but it is too stringent. It is too strong and difficult to achieve. In practical terms, we wish to transmit messages in such a way that no third party can have a significant, a substantial, a measurable advantage when trying to decide between two different messages. Recall that for perfect security, we enforced that the statistical advantage for a third party should be zero, exactly zero. Now let us relax that part of the definition by agreeing that the statistical advantage when trying to decide between two possible plaintexts after seeing the ciphertext should be less than a negligible quantity epsilon. So instead of exactly zero, the two probabilities now can differ by a tiny amount. Epsilon is a negligible quantity, and it can be defined in precise, in exact, in rigorous mathematical terms, but for us, for the moment, for the time being, just imagine that a negligible epsilon is an exponentially small quantity. So if we have, as attackers, any statistical sophisticated test which we could apply to two different plaintexts, just to compare if the ciphertext corresponding to those plaintexts are equal or not, then the probability of those two events is almost the same. Not exactly the same, but almost the same. This seems a tiny modification of the original definition of perfect security, but has in fact deep consequences from the point of view of the definition of security and the computational power of a possible adversary or attacker. The formal definition of semantic security involves this comparison of probabilities, but it is usually given in an alternative, more easier to understand as a form of an attack game between a challenger and a computational adversary. Let me specify how this attack game can be defined in our case. For us, and for understanding what security involves and means, an attack game is just a protocol, a sequence of operations between two entities, a challenger and an adversary. Given a cipher, a pair of encryption and decryption algorithms, and an adversary, let us define two possible imaginary experiments. And let's index the experiments as experiment 0 and experiment 1. Under experiment B, B can be 0 or 1, the adversary A chooses two messages, two plaintexts, M0 and M1 of his complete choice, and sends those messages to the challenger. The second part of the protocol is that the challenger chooses a random key and encrypts with that random key one of the two messages. The challenger encrypts message or plaintext 0 under experiment 0 and encrypts message 1 under experiment 1. The outcome, the encrypted message or the ciphertext Z, is sent back to the adversary A. The final part of the protocol is for the adversary. His task is to output an estimate, a guess of which one of the two messages has been actually encrypted, whether message 0 or message 1. If we measure the probability that the adversary wins the game, and he wins the game if his guess is correct, then the system is semantically secure, and this is again the formal definition, if the adversary cannot have other than a negligible advantage in guessing which one of the two experiments was the challenger running. In other words, if he cannot guess effectively whether the challenger has been running experiment 0 or experiment 1. This is a different form of the distinguishing between two possible encryptions of two different plaintext, but in this protocolized form, it's more easy. It is more amenable to analysis for verifying the formal terms in the definition of semantic security. In schematic form, let's represent this protocol or this attack game as two abstract boxes, the adversary to the right and the challenger running one of two different experiments to the left, and the sequence of messages exchanged between the adversary and the challenger. Initially, the adversary chooses two and sends a pair of plaintext M0 and M1 to the challenger. The challenger computes a random ciphertext because the key is random and because the adversary does not know whether experiment 0 or experiment 1 is being run, and returns the ciphertext. And finally, the adversary tries to output a guess, hat B, about which one of the two experiments was actually performed by the challenger. Here we understand the adversary and the challenger as abstract or mathematical entities, as black boxes, if you wish, and they only interact through the exchange of the messages represented in this functional block. Explain it in a different way, the definition of semantic security deals with the distinguishability between the encryption of two different plaintexts randomly chosen from the possible space of messages to encrypt. And the second fundamental part in the definition of semantic security relies on what we understand by a negligible advantage, the quantity epsilon by which the two probabilities can differ in this case. Differently from the definition of perfect security, here, for semantic security, we insist that the adversary has no unlimited or unbounded computational power. Instead, we assume that the adversary can use any efficient computational procedure, but not with unlimited resources. This is a very important idea to understand the meaning of semantic security in our context. Instead of allowing the adversary to use unlimited computational resources, which is not realistic, we only consider adversaries that can employ efficient computational procedures. And an efficient computational procedure is one which uses a limited amount of resources and employs time which is not exponential in growth. Apart from this, the difference in probability for the guessing which of the two experiments has been run is that the amount of statistical gain cannot exceed a very tiny number. The definition of a negligible number is to be understood as an exponentially small number. For instance, 2 raised to minus 200 is a tiny quantity and a negligible quantity for all practical purposes. Both features of semantic security system are very important for us, since in real settings we are only considering attackers who can use a large but limited amount of time and storage for breaking security of a practical encryption system, and which cannot gain other than a negligible amount of advantage when using that statistically efficient computational procedure. If you compare the two definitions, definition of semantic security and the definition of perfect security, you can easily see that semantic security is a weaker notion than perfect security. In other words, if a system is perfectly secure, then the same system is also semantically secure. Of course, the converse statement is generally not true. A system which is semantically secure is not necessarily a perfectly secure system. And we have some examples at hand. The one-time pad with constant length is a perfectly secure system, and therefore it is also a semantically secure system, but the variable length one-time pad is not a perfectly secure system. However, it is a semantically secure system, a property which, again, you can verify yourself quite easily. There are plenty of consequences of different possible interpretations stemming out from the definition of semantic security. In fact, we can characterize the properties of a semantically secure system in many different alternative and equivalent ways. Let me mention two of these equivalent ways for defining or for understanding the meaning of semantic security. We say that a system is semantically secure if it is computationally hard to predict any bit of the message. If we put the attack game as a bit guessing game, for example, for predicting the parity of the original plaintext, M0 or M1, this is equally difficult as guessing the plaintext in a whole. In an equivalent way, a system is semantically secure if, for a given adversary, it is computationally hard to recover the original plaintext from the ciphertext. Recall that in the definition given for semantic security, we insisted in distinguishing between two possible plaintexts, but without guessing the values of the plaintext themselves. Now imagine that we are trying to guess the values of the plaintext. This attack game is different from the original one, but is in computational terms equally difficult as the original game given in the first definition. Essentially, what semantically secure systems involve is the very intuitive idea that for breaking a semantically secure system, there is no other computational procedure more effective than trying one after one all the possible keys until having a match. So other than the brute force attacks as adversaries, there are no effective statistical procedures for breaking semantically secure system. And this idea is what ultimately matches our intuitive notion of when a system is really secure. For finishing this lecture, let me give you an application of these definitions and fundamental ideas by explaining a combined system known as nested encryption and onion routing, which is interesting in itself because with nested encryption and onion routing is by which the Tor, the onion routing dips. In other words, nested encryption and onion routing are the fundamental building blocks for transmitting traffic on the deep web. Let's imagine this setting. Suppose we have two parties, Alice and Bob, which wish to exchange a message in an anonymous form. That is, without disclosing the sender's identity. Imagine that Alice is the sender in this case, and she wants to transmit an encrypted message to Bob, but she does not want Bob to know her identity. So Bob should receive a message, and he should have no way to discover that Alice was actually transmitting the message to him. For achieving this, both of them, Alice and Bob, can agree with a third person, Carol, who acts as an intermediary party between the two. So using the intermediary Carol, Alice takes the original message, prepends the message with Bob's name, with Bob's identity, and encrypts with Carol's key the pair of values, Bob's identity and the plaintext M, and sends this encrypted message to the third party, to Carol. Since the key is secret and symmetric and shared only by Alice and Carol, only Carol can decrypt the message. So she extracts the encrypted message, which is the pair Bob and plaintext M, and encrypts again the message, the plaintext M, with Bob's private key, which is only known by Carol, but not by Alice. So in the end, Bob receives an encrypted message and he uses his encrypted key to recover the original plaintext, but he does not know by any means who is sending this message to him. In other words, there is no way for Bob to discover that Alice was the creator of the message he has just received. However, this simple system using an elementary third party has two problems. The first one is that if Carol and Bob collude, if they are in agreement beforehand, then Bob could find out Alice's identity, just simply asking Carol who sent the message to her. And the second problem is that if an eavesdropper has access to the two channels, the first one between Alice and Carol and the second one between Carol and Bob, then the eavesdropper can learn truthfully that Alice actually sent a message to Bob. These two problems, however, can be solved by using a smart combination of nested encryption and onion routing, using not only a single third party, but a chain of two or more intermediaries between Alice and Bob. So the two problems, let me recap these ideas, are the following one. The first one is collusion. We want to avoid that the third party agrees with the receiver and discloses the identity of the original sender. And the second problem can be solved through mixing by using not a single intermediary, but a collection of intermediaries in a chain of encrypted messages. In fact, the first part for collusion also needs to use two or more intermediaries for exchanging messages between Alice and Bob, and mixing the possibility of not revealing information for an eavesdropper watching all the point-to-point channels is to randomly mix in time the sequence of messages to be transmitted. Let me explain in more detail how collusion and mixing are used in Tor, the onion routing, which is the fundamental procedure for transmitting traffic in the deep web, as I said at the beginning of this example. Onion routing is just a combination of nested encryption plus source routing. So suppose that between the sender S and the destination D, 2 points, for instance, two computers in the deep web, there are set of intermediate points, H0, H1, and so on. The first point, H0, is the source itself, and the last point, Hn, is the destination itself. Then imagine also that this path through the intermediate nodes in the network is known in advance. In other words, the source chooses the route to be followed by the message, plaintext or encrypted. In this case, for our purposes, encrypted. Now, for sending an encrypted message along this route, the source just picks the plaintext M, the original message, and performs a sequence of encryptions, one after the other. For the first step, the sender encrypts with the private key of the last hop, the destination, the plaintext M. Remember that the complete route is known in advance by the sender, so he knows all the intermediate points, and we assume that he also knows the private keys used at those intermediate points. The result of the first step of encryption is the ciphertext corresponding to the plaintext M with the private key of the last hop, in this case the destination D. To this ciphertext, the source prepends the identity of the last hop and encrypts this combined message using the private key of the next to last intermediate point, and so on, going backwards until encrypting the combination using as the last step the private key of the first hop in the route. Note that at each step the source prepends the identity of the next hop in the path to be followed by the encrypted message. This chain of encrypted messages is then transmitted to the first hop, from the inner encryption to the outer encryption. Now, let's see how the first hop H1 operates. The first hop receives the message you can see in the equation in this slide. Because the outer encryption has been done with the private key of the first intermediate hop, he can decrypt the enclosed message and recover two pieces of information. After decryption at the first intermediate hop, this intermediate node can learn the identity of the next hop, H2, and the message to transmit to the next hop, which is the second part in the decrypted message. So he sends the encrypted message to the next hop, and so on. At every intermediate point, one layer of encryption is undone. And this is why this is also known as onion routing, because at each intermediate point, one removes one layer until reaching the destination. Note also that this form of nested encryption and onion routing achieves or solves the first problem, collusion, because no party, in particular the destination point, can learn nothing about the original sender in this message, S, because the intermediate points only know the previous hop, but not the original one. This is the same to say as only the first intermediate hop knows S, the identity of the source, but further intermediate nodes in the downwards, in the downstream direction cannot learn nothing about S identity, only about the identity of the previous hop. So collusion is solved perfectly. For the second requirement, mixing, Imagine that with this form of nested encryption and source routing, not a single message is being transmitted, but a sequence of messages are being transmitted through the same or through different routes or paths. So in this case, at a given intermediate point, let's say h sub I, we can receive at a given time instant a collection of encrypted messages to forward to different destinations. Imagine now that for forwarding those encrypted messages to the destinations, the intermediate node, h sub I, randomly picks one of the pending messages and transmits this message to its next hop. An eavesdropper who could be watching all the communication channels could not discover the exact sequence of sender and receiver because the intermediate points randomly mix the order in the sequence. So this second requirement is also satisfied by using a randomized transmission scheme at each of the intermediate points. In real-world technology, this is exactly the procedure used in the deep web, also known as Tor, T-O-R, are the acronym for the onion routing, for transmitting messages anonymously, and explains very easily how using symmetric encryption and an intelligent and smart form of encrypting one after another in layers, plus using source routing from the original sender, can provide complete anonymity for sending messages through the internet and in particular through the deep web. I hope you have understood from this lecture several important ideas as starting points in this course. The first important idea to remember is the definition of a ciphering operation. In particular, the definition of what is known as a Shannon cipher, a pair of algorithms which are inverses one of the other. The correctness property is the essential part in the definition. Secondly, the definition of what perfect security is. Perfect security can be very easily defined, but it is an ideal notion of security because only with impractical system is possible to achieve perfect security. Since perfect security has some serious limitations and it's too strong for practical encryption systems, we have relaxed the definition and presented semantic security in terms of computational power of a given adversary and in terms of protocols or attack games. Semantic security is fundamentally the same idea, but introduces small or negligible difference in the statistical distributions of the plain text or the ciphertext and a computational limit on the resources that the adversary can use to break the system. And as an example of all these ideas, we have seen that symmetric encryption plus nested application of the encryption algorithm can provide complete anonymity for sending messages through a network like in the deep web. In the rest of the lectures in this course, we will discuss in depth different specific algorithms to achieve semantic security in practice. They are much more sophisticated than our elementary substitution or one-time paths, and they can be proven to be semantically secure, and the definition of semantic security can also be refined in different ways to provide even stronger assumptions and making the system even more secure than against a brute force attack. But this is the topic of the future lectures. I hope you have time to study and analyze this definition and to steer your interest in the course about information security. Thank you very much for your attention.